Okay, in this problem, we have a wire that's wrapped 5 times around a long solenoid that has 465 turns per meter. It also has a cross-sectional area of 35 square centimeters. We're asked to find the mutual inductance between these two conductors. So in order to figure this out, we have to calculate the flux when currents run through one of the inductors that gets induced in the other. Now, given that we're not given much information about the wire that's wrapped around 5 times, we're going to have to calculate the flux that's induced by a current through the solenoid. So let's go ahead and do that. Before doing so, let's write down the expression for mutual inductance. Mutual inductance is defined as the number of turns for one of the conductors, in this case a long wire, times the flux through that conductor, at least one loop of that conductor, divided by the current through the other conductor. So in this case, number 2 would be the wire loop, and number 1 would be the solenoid. So let's go ahead and proceed to calculate this. Let's go ahead and look at a top view. I have a top view. I have the solenoid, which wraps around and around and around and around. And that's going to produce a B field, which is uniform inside the solenoid, points out of the page. And then around that, I have wrapped wire loops. In fact, I have 5 of them. And what I need to do is I need to calculate the flux through the wire loop. Well, I can see that in the ideal sense anyway, all the magnetic field here is contained within the solenoid. And so in order to calculate the flux through the wire loop from the solenoid, I just need to know the B field of the solenoid times the area through the loop where the B field's non-zero. And it turns out that this area, in fact, is the area of the solenoid. I'm not using the area of the loop because the B field is 0 outside the area of the solenoid. So the only contribution to the flux is the B field that's traveling through the area of the solenoid. All right, so let's go ahead and calculate the magnetic field of a solenoid. That's just mu naught times N times the current through the solenoid, in this case I1. So what this means is the flux through the wire loop is going to be the area of the solenoid times mu naught times N times I1. Okay, now in order to calculate the mutual inductance, then I just have to use this expression for the flux. Remember, it's N2 phi-B2 over I1, which gives me N2 times the area of the solenoid times mu naught times N. Okay, I can put the numbers in here. N2 is 5. The area is 35, square centimeters. And I have to convert to square meters in order to keep consistent units. And then after I made that conversion, I multiply by mu naught. And then finally, I multiply by the number of turns, which is given as 465 per meter. Multiply all these things together, and I get 10.2 times 10 to the minus 6. This turns out to be joules per amp squared, or 10.2 microhenries.